Welcome to Mastering Data Analysis, Introduction to SPSS and Applied Econometrics. This presentation is designed as a step-by-step guide to help you navigate through sample files, perform essential operations, and create insightful visualizations. As Carl Pearson famously said, statistics is the grammar of science, underscoring the critical role of data analysis in understanding our world. This comprehensive guide has been compiled by the Recode Econometrics Group, and we are excited to share this knowledge with you. In economics, we often start with a hunch or an assumption, like those for predicting wage gaps, assessing inflation, or optimizing portfolios. This initial intuition is often insufficient, being filled with biases, hunches, and speculation, as visually represented by the word cloud on the left. We deal with complex variables, such as GDP, educational attainment, and market volatility. Quantitative analysis is the crucial step that transforms this raw data and gut feelings into concrete evidence. It moves us from merely assuming a relationship to statistically proving it, typically with a p-value less than 0.05. For example, if we believe advertising spending increases sales, quantitative analysis can take actual data and give us a precise measure of that relationship, like an R-squared value of 0.85, indicating that 85% of sales variation is explained by ad spend. Without this rigorous approach, economic policy is merely guesswork. Tools like SPSS are vital for bridging the gap between raw data and generating actionable insights. This slide presents a clear methodology decision tree to help you select the appropriate statistical analysis method. The starting point is always the type of your dependent variable. Is it continuous, scale, or categorical, nominal? If your dependent variable is continuous, scale, your next step is to define your research goal. Are you comparing two groups, in which case you'd use a t-test, comparing more than two groups, leading to ANOVA, or predicting values, which calls for regression? If your dependent variable is categorical nominal, you'd either test an association using chi-square or predict probability using logistic regression. As highlighted by the golden rule on the side, your analysis method is strictly dictated by the type of data you have, nominal, ordinal, or scale, and your specific research question. This slide summarizes some common SPSS methods, their functions, and practical economic applications. Starting with descriptive statistics, these are your foundational tools to summarize data using measures like mean and standard deviation. They're perfect for demographic overviews, giving you a quick snapshot of your dataset. T-tests are used when you need to test differences, specifically to compare the means of two distinct groups. For example, comparing the effectiveness of drug A versus a placebo, or analyzing income disparities between retired and working individuals. Correlation helps us establish relationships. It's used to see if two variables move together, like examining the link between education levels and salary. Finally, regression is a powerful method for prediction and forecasting. It allows us to model how one variable can predict another, such as forecasting sales based on advertising spend. An interesting note from our source insight: even seemingly complex analyses, like Bland-Altman plots used to compare two measurement methods, fundamentally rely on simple underlying logic, namely comparing the means and differences of two measurements. This highlights how advanced techniques often build upon basic statistical principles. These methods, while distinct, often complement each other and rely on fundamental statistical concepts. Let's delve into these core concepts next. The mean, represented by X bar, is the central tendency or balance point of your data. The standard deviation, represented by S, measures the spread or variability of the data, indicating how risky or variable it is. The p-value, or p, is the probability that your results happen by chance. The rule is that if p is less than 0.05, the result is statistically significant, meaning you can be 95% confident that the relationship you observe is real and not just a fluke of the sample. First, normality. For many tests, your data should roughly follow a bell curve or normal distribution. Second, homogeneity of variance. When comparing groups, their spreads or variances should be similar. In SPSS, Levine's test is used to check this. Third, independence. Each data point should be independent, meaning one participant's measurement doesn't influence another's. Fourth, linearity. For correlation and regression, the relationship between the variables should be linear, meaning it can be represented by a straight line. Running a test without meeting these assumptions leads to invalid results. Always clean and check your data first. When you look at regression output, first check the direction. The sign, plus or minus, of the unstandardized B coefficient tells you if the relationship is positive or negative. Next, look at the magnitude. This is the value of the B coefficient itself. It tells you the size of the effect. For every 1 unit increase in the predictor, the outcome variable changes by B units. Then, check for significance. The sig column is the p-value. If it's less than 0.05, the coefficient is statistically significant, meaning the effect is reliable. Finally, the r-squared, or r-squared value, tells you the explanatory power of your model. An r-squared of 0.60 means that 60% of the variation in the dependent variable is explained by the independent variables in your model. In the context of economic meaning, remember that statistical significance does not equate to economic significance. A tiny effect can be statistically significant, but still meaningless in a practical sense. Always focus on the magnitude of the effect. This slide highlights the 2 critical views in the IBM SPSS Statistics data editor for modern academic and clinical data analysis. First, we have the data view, which functions as your primary spreadsheet. Here, rows represent individual cases or observations, while columns are dedicated to your variables. For example, if you're tracking patient outcomes, each row would be a patient, and columns would hold their medical readings or demographic details. Second, there is the variable view. This is where you define the fundamental properties of each variable, such as its name, data type, like numeric or string, and measurement level, such as scale or nominal. A crucial navigation tip for efficient workflow is that you'll spend approximately 80%. Nearly every statistical analysis you perform in SPSS follows a simple, memorable hierarchy. You will always start by clicking on the Analyze menu at the top of the screen. From there, you select the general type of test you want to run, such as compare means or regression. Finally, you choose the specific test from the submenu, like Independent Samples t-test. Memorizing this path, Analyze, then Test Type, then Specific Test, is key to navigating SPSS efficiently. To run a correlation analysis, you would follow the path. Click Analyze, hover over Correlate, click Bivariate. This 3-click process is standard for almost all procedures. Let's put this into practice with a complete workflow, from loading data to running a test. This slide details the first step in our workflow, loading data. We begin by navigating to the Open Data dialog box, which allows us to browse for our datasets. For practice, SPSS provides built-in sample files. You'll typically find these in the Samples folder, often located within your SPSS installation directory. A highly useful example is demo.sav. Opening this file provides instant access to a pre-formatted dataset, saving you the time of manual data entry and allowing you to immediately dive into analysis. The first step in any analysis is to load your data. SPSS comes with built-in sample files, which are perfect for practice. You can find them in the Samples folder within the SPSS installation directory. A common file is demo.sav. Before running any complex models, you must perform a sanity check. The best way to do this is by running descriptive statistics. This simple step helps you spot impossible values or data entry errors. For example, if you see a mean age of 150 or a maximum value of 999 for a variable measured on a 1 to 5 scale, you know there's an error that needs fixing. This prevents the garbage in, garbage out problem. After setting up your data and running analyses, visualizing your findings is crucial. In SPSS, you can create various charts using the chart builder, as seen on the left. Once a chart is generated in the output window, it often appears in a basic, raw format by default. To enhance its appearance and make it publication-ready, you'll need to use the chart editor. Always double-click the chart within the SPSS output window to open the chart editor, which provides extensive options for professional formatting and customization. This slide visually demonstrates how to run an independent samples t-test in SPSS, building on our previous discussion about hypothesis testing. On the right, you can see our clear hypotheses. The null hypothesis, HO, states that income is the same for retired and non-retired people, implying no difference between the two groups. Conversely, our alternative hypothesis, H1, posits that income is indeed different. In the SPSS dialog box on the left, we've set up the test by designating household income, as our test variables. This is the continuous variable whose means we want to compare. Below that, retired 01 is selected as the grouping variable. This categorical variable separates our data into two groups, retired 1 and non-retired 0, allowing us to compare their mean incomes. The Options and Bootstrap buttons provide further customization, but for now, the key is the correct assignment of our test and grouping variables to address our research question. The output table gives us everything we need to interpret the independent samples t-test. First, we examine Levene's test for equality of variances. The p-value, or sig, for Levene's test is 0.432, which is greater than our significance level of 0.05. This tells us that we can assume equal variances, so we should refer to the top row of the subsequent t-test results. Next, we look at the t-test for equality of means. The sig, two-tailed, column for the t-test shows a p-value of 0.000. Since this value is less than 0.05, we conclude that there is a statistically significant difference in mean income between the two groups. Finally, to understand the direction and practical meaning of this significant difference, we consult the group statistics table. Here, we see that the mean income for non-retired individuals is $56,800, which is substantially higher than the mean income of $31,200 for retired individuals. The verdict is clear. It's crucial not to just report the p-value. Instead, explicitly state the direction of the difference. In this case, non-retired individuals earn significantly more on average than retired individuals. This slide highlights a crucial pro tip for working with SPSS. Always use the Paste button instead of OK. When you click Paste in any SPSS dialog box, it writes the underlying command syntax into a separate syntax editor window. This is visible in the image, showing commands like getFile, frequencies for variables like gender, and descriptives for income with mean and stddev statistics. This syntax editor serves as your invaluable audit trail. It records every step of your analysis, making your work transparent, reproducible, and easy to review or modify in the future. It's a best practice that ensures the reliability and consistency of your research. This slide provides essential resources to further your learning in SPSS and applied econometrics. These include foundational texts like How to Use SPSS, a Step-by-Step Guide by Cronk, and IBM SPSS Statistics 29 Step-by-Step by George and Mallory. Also, Discovering